Welcome back, everyone. Our next speaker is Lisa Lorenzen. Lisa has been a very prominent member of the SAPSA community for a long time. I struggled to find a way to introduce Lisa other than to say that her technical mind and the way that she thinks and solves problems blows my mind. In my introduction yesterday, I said that we like to challenge the speakers and that you may come across a circumstance where a COSAC speaker has the enormous professional integrity to say, this subject is new, I am not the world expert, there may not even be any experts. And I believe that that is the position that Lisa's going to take today, which is in itself a privileged part of COSAC. So Lisa, stage is all yours. Thank you very much, and thank you for wearing the official shirt.
Yes, thank you, David. It's a pleasure to be here. It's a pleasure to continue to participate in COSAC. And I also want to say hello to all of our friends at Kilishi House, Dee and Sinead and Orla and the staff there. Thank you for making us feel so at home, and I hope to see you again next year. So I gave this talk at COSAC 2019, and I was thrilled when David gave me the go-ahead to revisit it for the COSAC Connect audience. As he said, this is not my area of expertise. And this is not exactly new, although some of the information is from last week, but the bulk of the material is almost a decade old at this point. So it's a real balance between why has this been around so long? Why are we still talking about it? And what does it mean for us today? When we look at my background, I am not speaking to you today on behalf of Zscaler, and I'm not speaking as Director of Transformation Strategy. This is somewhere between a book report and a love letter. I don't work in this space, and I don't even really work anywhere near it. I didn't do any of the research that I'm going to talk about. And honestly, a lot of it is so far outside my swim lane that I only superficially understand it. But it's really fascinating to me, and I want to share that fascination in hopes that you will find it equally interesting. So the new part. I hope that everyone by now has heard of Zero Logon. It's been in the news since about the middle of August. And it is a new vulnerability that is an exploitable crypto implementation mistake, where 1 in every 256 randomly generated keys results in the encryption of a plain text consisting of all null bytes, giving you a ciphertext that's also all null bytes. And this vulnerable cryptographic protocol implementation, unfortunately, is used as an authentication mechanism in the NetLogon protocol. The NetLogon protocol, which is used in Active Directory, mostly by workstations and servers, to communicate with domain controllers over a secure channel. So you would think that this might be a bit of a big deal, and you'd be right. Microsoft started patching this in late August 2020, and by mid-September, concern about this vulnerability was great enough that the US Department of Homeland Security issued an emergency directive instructing all federal agencies to patch the vulnerability by September 21st at the latest. And we found out why, because a couple days later, Microsoft warned everyone that Zero Login was now being exploited in the wild. So how do we get here? What is the root of this problem? One of the challenges is, because of this implementation error, it means that if you send a challenge that is made up of 8 bytes of zeros, and you keep retrying that for 256 times, eventually the server will hit that point where the null bytes in ciphertext result in the null bytes in the plain text, and you get in. So that's kind of a big deal. How does this come about? When we look at it, this immediately reminded me of a talk that I saw at ShmooCon in 2012 called The Science of Insecurity. And ShmooCon is a conference presentation, it's a conference in Washington, DC every year. And it's one of my favorite conferences because you find that you get a whole variety of different topics. And I try to go every year to at least one talk that is completely outside of my experience. Some of my favorite talks I've seen that way. And in 2012, it was this one. So when we look at what they were talking about in this science of insecurity, the challenge is that insecurity is about computation. Any assertion about what you can trust about a system It's basically, will it drop a shell on a system if you send it data? Will it expose your data? And all of that comes down to what a system can or cannot compute. So when we think about it, every system decides what is good or bad. And that means that the system may be making a well-founded decision, or it may not. Blindly accepting input is a decision too. So exploitation is basically unexpected computation. And we should consider an exploit to be a program, coded in crafted input, that runs on the target and exposes new computational structures that we don't expect in the target. So this means we can basically send information to a system and have it do something that the original programmer didn't intend. And this basically blew my mind. At the time, I'd been working in technology for over 15 years, and specifically in InfoSec for over a decade, but that talk fundamentally changed my perception of cybersecurity. So in that talk, they mentioned a previous ShmooCon talk on how dwarf is Turing complete. And that looked like a fun rabbit hole to go down. So I decided to go check that out. And by the way, I do want to note that, there we go. The archive for ShmooCon is available on archive.org, and it is amazing. You can find almost all of their previous conference talks there, any of them that were not given under NDA. And there's just some great material there going back the 10 or 11 years that the conference has existed. So when I went to find this talk, I realized I'm going to like these guys. They translated their title slide into Tolkien Dwarven runes, which completely got me off track because I was a medieval studies major and a huge Tolkien nerd. So as soon as I popped this up, I hit pause on the video and I started seeing whether I could still read Dwarven in line. So eventually I get over this and I get to a point where I actually want to see what they have to say. And it looks like a talk that's going to be interesting. The first content slide was an executive summary. I'm hanging in there. And then they start talking about bytecode and stacks and return to libc attacks. And did I mention that I was a medieval studies major? So I may have been working in IT and InfoSec for 15 years at that point, but I did not code and I still don't. So clearly I needed more background. In the original Science of Insecurity talk, Sergey and Meredith had also mentioned a talk by Halvar Flake at Infiltrate 2011. And I figured I'd go check that out and see if it gave me the background I needed. And by the way, I know I'm ripping through this. All of these talks are online. Very often there are papers, PDFs, even the slides available for them. And my presentation PDF will include my speaker notes that have links to all of these. So if you're interested, you can follow the same breadcrumb trail that I did. Anyway, so I start watching Halvar Flake's talk, and I did a little better with that one. You know, I caught a few bits here and there rather than being totally at sea. And I still didn't really understand all the fundamental points, but the concepts keep getting more and more interesting the more I understood. So now I'm going to show you how deep the rabbit hole goes. And we're going to explore this in a little more detail. We're going to start again with Sergey and Meredith's Science of Insecurity talk. And the next handful of slides are my attempt to summarize what I learned from that talk. So anything you see that's interesting comes from them. And frankly, anything that doesn't make sense is entirely the translation layer. My goal here is really to get you interested enough that you want to go watch it for yourself. So the illusion that your program is manipulating your data is powerful, but it's an illusion. The data is actually controlling your program. And this was another rabbit hole. Mike and I were talking about this, and he remembered a quote that data and computation are inseparable. We thought it was Alan Turing, but we couldn't find a citation. So if anybody knows who actually said that and wants to drop it in the comments or hit me up on LinkedIn or Twitter, I would love to have a source for that because it's absolutely relevant here. So when we think about software, all software is composed. Programs consist of many components, and they have to accept messages that come in over some communication medium, and they also have to reject the messages that they can't accept safely. When programs communicate, they really need to make sure their parsers are interpreting things identically on both sides. If your parser on one side doesn't interpret identically what was sent on the other side, you may end up with state that wasn't intended. And so this is where undecidable problems come in. Is this input good or can it hurt? You have problems that can't be solved, like answering that question, and that is the root of insecurity. Why? Well, we tend to think that a parser is processing the input, but really the input is executing on the parser. And this is not just a limited concept. So you have packets that execute on TCP IP stacks. You have malloc and free executing on heap managers. You have binary format metadata that execute on the linker loader. And you have page tables, global descriptor tables, or interrupt descriptor tables that execute on the MMU. Blah, 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 ginger, right? I understood the first bullet when I started off and none of the rest. So that's what we're going to explore today. But we need a little bit of background first. So we're going to start off with the concept that inputs are a language. IP packets are a language. They have nested structures and they execute on the stack. They have length fields, so they're weakly context sensitive. And the stack is a recognizer at every layer of protocol. For servers, valid requests make a language. All APIs have a grammar, whether or not they've been formally defined that way. So APIs are a language. And we get context sensitivity again here. Which bytes are data and which are metadata? So when we think about it, languages have a grammar, and understanding the grammar of that language helps you to first recognize and then interpret that language. Some languages have more context than others, and if you have more context than your code can deal with, you become a cog in a weird machine. The input you get might cause your program to do something you don't expect, and you'd be better off with a simpler input language. All right, let me dive back in here. Language theory. So Noam Chomsky, the father of language theory, basically said there is a hierarchy of language. Regular languages are very easy to work with and very decidable. If you have two regular expressions, you can decide in a reasonable time whether they both express the same language or not. Up the stack, context-free languages are more complex, but still finite state. So there's a grouping thing where Perl regular expressions can recurse on themselves, and that makes them a context-free grammar. Context-sensitive languages get even more complex. They can refer to other parts of the tree. So I have a payload. It has a length that was specified earlier in the packet. It refers back to that to make sure the length field is the same length as the payload that I've got. And when this fails, you get padding attacks. The most complex languages are the recursively enumerable languages. And these are not decidable, whether they're equivalent. To understand why, we need to turn to a historical concept. Oh, sorry about that. There's different ways to address these languages. You have different levels of complexity required to process languages at each layer. So when we get to the Turing machine, it helps to understand what a Turing machine is. Language recognition is really critical because some languages are harder to recognize than others. And for some of these languages, it's not decidable. As your programs are composed, so is your data. And the regular expressions and finite state machines allow you to express simple nesting. But you can't achieve the complicated behavior you want without nesting some complexity into the data. And when you're performing validation, you must use the appropriate strength of mechanism to validate. So you need to match regular with regular and context-free with context-free. Now we come to the Turing machine. A Turing machine is a theoretical generalized computer, and it's composed of a tape on which symbols representing instructions are printed. The tape can move backwards and forwards in the machine, and the machine can read the instructions and write the resulting output back onto the tape. So despite the simplicity, a Turing machine can simulate any computer algorithm. And a Turing complete system means a system in which a program can be written that will find an answer when you ask it a question. although there may be no guarantees about runtime or memory. So if a system is Turing complete, that means that in principle, it could be used to solve any computational problem, even though it may not be in practice. And the challenge comes that Turing complete systems appear in places that we would never expect them. And sometimes they're not helpful there. So one thing that a Turing machine cannot do is it cannot take another Turing machine and decide if that second input, the Turing machine that it's processing, will ever terminate or loop. This is fundamentally against the laws of nature. If it doesn't halt, then it halts. If it halts, then it doesn't halt. So does it halt or not? The answer is that there is no answer. It's the computer programming equivalent of saying, I always lie. If it's true, then it's not true. And if it's not true, then it's true. So the halting problem, as it's called, is uncomputable. And trying to decide an undecidable problem turns out to be the root of a lot of insecurity. So the challenge here is any sufficiently complex input is indistinguishable from bytecode. And the corollary is that any code that receives such input is indistinguishable from a virtual machine. You see where this is heading, right? What happens when input recognition fails? Let's take some examples. Primitives get exposed, memory corruption, implicit data flow, and unexpected control flow result in behavior that the original programmer didn't intend. So SQL injection is a recognizer failure. What escapes the escape symbol? Being able to slip in and unescape the escape symbol is a failure of the recognizer. Not understanding that you're dealing with a language problem of what a valid escape symbol is and not building the right automaton to address it is how we get SQL injection. Memory managers have heap metadata exploits that abuse the context sensitivity. So heaps are complex and they're exploited because of metadata overrides. And I love this. This exploit technique is called heap feng shui. I think that term was coined by Alexander Sotorov, and he's got a lot more material on that. Buffer overflows overwrite return pointers on the stack. And this works because valid stacks are a language. The language is so complex because to unwind the stack frames, you need a fully Turing complete virtual machine. And this is what the dwarf standard provides. So we'll get back to dwarf in a minute. In each of these cases, there's just way too much context. A piece of code looking into the data cannot make a determination whether the next step, whether it's patching a double linked list or writing this buffer, whether that step will be correct in the context it's in. So you get a more powerful, programmable execution environment that was intended or even expected. Input into a program drives changes in state in the input handlers. You have to trust your execution model that those state changes proceed in a way you desire. So the structure of a program is basically some basic blocks are recognition checks, sanity checks, the parser, the recognizer, and some blocks are execution, things you want to do with the data, the processing components. When people write code, they don't generally think about recognize and then parse and then hand off to execution. So code ends up getting written piecemeal. A little recognition here, a little parsing there, some execution, and then you recognize again, and fragmentation attacks take advantage of this. If you don't do all of the correct checks, then you get memory corruption, you have some expectation by a block in the code that's not fulfilled. The block does something unexpected, and when unexpected computation occurs, you can get implicit data flow to other blocks. So the computational structure can be driven by crafted input, and we get a weird machine, a more powerful computational structure than intended, and it's driven by crafted input that is running the actual exploit. So this term was apparently coined at an RSA security seminar in Berlin in 2011. When you intermingle input recognition with state, you open yourself up to logical flows you're not expecting. And vaguely understood input languages are then the mother of 0 day. If you don't understand the input language, you can't determine whether the message is valid. Even if your input language is understood, combining the code flow of input handling and input processing opens you up to problems. So if you look at this problem from the exploiter point of view, what you get out of your program is execution primitives that you can steer with your input from state to state and transition to transition that were not meant to happen in the original code. You get an automaton that was implicitly there, and you explicitly instantiate it with your crafted input. Sergey Bratis collected a bunch of examples of this in his Weird Machine Zoo, along with links to other collections, such as Accidentally Turing Complete. And I'll just note, when I was trying to find a picture to represent this, I stumbled across an artist page on DeviantArt for an artist named A Mechanical Mind. It's the perfect representation to me. He has a huge collection of these critters. They're made of watch parts and other artifacts, and they're all amazing. So check him out too. This principle applies all the way up the OSI model. And we can start at the bottom and work our way up. In 2011, Travis Goodspeed gave a talk on packet-in-packet, a physical layer injection attack. And he framed this relative to War of the Worlds, which was initially a radio program in the United States. So this was back when radio programs were a common entertainment. People would listen to them in the evenings. And Wells crafted a radio program that omitted the initial station identification and the standard introduction. It jumped right into the story. So he basically misled the listeners into thinking that they were listening to legitimate news broadcasts of an alien invasion rather than just that evening's entertainment. So ensuring that the listener missed the starting broadcast announcement breaks the encapsulation on the radio that's intended to prevent such confusion. And that's just the way a packet-in-packet injection relies on the start of a frame to be missed in order to break the OSI model encapsulation. So let's drill into this a little. Packet-in-packet is an escaping problem, the physical layer. Zigbee has packets with fields in the header and then a body. And one of the header fields is a sink. So you get a preamble, a sink, and a body. The packet starts wherever the sink is. What happens if you put a sink in the body? Hardware has no idea what to do about it. It's not the hardware's job to know anything about layer 2. If a symbol error occurs in the preamble or the sink, the receiver can think that the body is a new packet. If the preamble or the sink get munged, same thing can happen. So it picks up another layer 1 packet that's just embedded in the body. Now you can eliminate this problem with encryption, so even WEP is still good for something. If you can attack layer 1 in packet radio, where else can we do it? How about Ethernet? So this is a very esoteric technique. Excuse me, I jumped too soon. It requires custom hardware, but the same concept still applies. If we start moving up the stack, we can head up to layer 3. And now we're looking at BGP. This is where it starts to get into familiar territory for me. This is a paper describing a mapping between BGP and a logic circuit. Simple networks with routers that have elementary BGP configurations can simulate logic gates, clocks, and flip-flops. And they talk about how to interconnect them to simulate arbitrary logic circuits. So under reasonable assumptions on message timings, BGP has the same computing power as a Turing machine. You can investigate a new method for studying the complexity of analyzing BGP configurations and exploit such a method to give new complexity bounds. That means that if message timings are unrestricted, BGP can simulate a combinational logic circuit. This is just madness, right? It's better because the really good stuff is at layer 7. So now we wrap back around to that original dwarf talk, exploiting the hardworking dwarf. All GCC compiled binaries that support exception handling include dwarf bytecode. This describes the stack frame layout. and it's interpreted to unwind the stack after an exception occurs. The runtime process image will include the interpreter of dwarf bytecode. It's part of the standard GNU C++ runtime. The bytecode can be written to have the interpreter perform almost any computation. Doesn't this sound familiar? It's Turing complete. So dwarf expressions function essentially like an embedded assembly language in a place where you'd least expect it. It's a Turing complete stack-based machine. The computation works like an RPN calculator. You can backdoor a program so it runs normally until an exception is thrown. And you can return from an exception anywhere in the program with control over most of the registers. You modify no executable or normal program data sections, and you can hijack the exceptions to get a shell. Another great example here is weird machines in ELF. So Rebecca Shapiro created a Turing machine in Linux from relocation data in an ELF file, executable and linking file format. You can hide code in ELF metadata for ping and get a root shell. ELF is everywhere. Related OS and library code is run whenever processes are set up and serviced, i.e. dynamically linked. The loader is the stage manager for every executable, and the loader can be tricked into performing any computation by presenting it with crafted but otherwise well-formed ELF metadata. So you're not even sending it anything illegal. It's just specially crafted ELF relocation and symbol table entries that can act as instructions to coerce the linker loader into performing arbitrary computation. She provides a proof of concept method of constructing ELF metadata to implement the Turing complete brainfuck language primitives. And I have to say that anyone who names a programming language brainfuck is being more honest than most coding environments. She demonstrated a method of crafting relocation entries to insert a backdoor into an executable. Another one of these examples is the Page Fault Liberation Army. It's a Turing machine created in the x86 MMU from address translation. There's actually a demo on GitHub where you can fly a glider around a screen. And the idea here is that trust analysis, determining that a system will not execute some class of computations, typically assumes that all computation is captured by an instruction trace. But it's possible to perform powerful computation on x86 processors without executing any CPU instructions at all. So the paper's authors demonstrate a Turing-complete execution environment driven solely by the i32 architecture's interrupt handling and memory translation tables, which the processor is trapped in a series of page faults and double faults without ever successfully dispatching any instructions. The hardwired logic of handling these faults is used to perform arithmetic and logic primitives, as well as memory reads and writes. This mechanism can even perform branches and loops if the memory is set up and mapped just right. So they provide a proof by construction that the Intel MMU's fault handling mechanism is Turing complete. They constructed an assembler that translates move, branch if zero, and decrement instructions to csource that sets up various processor control tables. After the code has executed, the CPU computes by attempting to fault without ever executing a single instruction. Optionally, the assembler can even generate x86 instructions that will display variables in the VGA frame buffer and cause control to be transferred between the native display instructions and weird machine trap instructions. This is crazy. But all of this was from 2011 to 2013. Pushing a decade or so ago in some cases. Surely this has all been fixed by now, right? Apparently not. So Thomas Dullian, the presenter here, is Halvar Flake of that Infiltrate talk 7 years previous. And in December of 2018, he was still talking at RURSEC about weird machines and exploitability. So, how do we address these issues? Are we just doomed to keep watching the InfoSec world burn? One way to handle it is to tackle them at their source. there's a group called LangSec. It's both a group and an approach. And the language theoretic approach regards the internet insecurity epidemic as a consequence of ad hoc programming of input handling at all layers of network stacks and in other kinds of software stacks. LangSec posits that the only path to trustworthy software that takes untrusted inputs is treating all valid or expected inputs as a formal language and treating the respective input handling routines as a recognizer for that language. The recognition must be feasible, and the recognizer must match the language in required computation power. That's a mouthful. Fortunately, on their website, they've broken it down into a few key tenets for us. So the first one is full recognition before processing. Every piece of software that takes inputs contains a de facto recognizer for accepting valid or expected inputs and rejecting invalid or malicious ones. This recognizer code is often ad hoc, spread throughout the program, and interspersed with processing logic. They call it a shotgun parser, which is hysterical to me. This lends the processing logic to exploitation, and it gives programmers false assumptions of data safety. The solution is to apply full recognition to inputs before processing them. Another step is to reduce the necessary computing power. Unneeded computing power in input handling code is a handout to attackers. Reduce the computing power needed for your protocols, and you reduce your parsing exposure to the necessary minimum. The power that isn't there can't be hijacked. Once created, the glut of computing power cannot be destroyed because of backward compatibility. Repackaging of insecurity goes on forever. Fight it at the origin. Reduce the computing power demands of your protocol. So hard to parse protocols require complex parsers. Complex, buggy parsers become weird machines for exploits to run on. And you can help stop weird machines by using a protocol that is context-free or regular, i.e. low on the complexity hierarchy. Regular languages have a finite state machine that gives you very simple nesting structures. A finite amount of recursion is okay. Infinite recursion, like XML or HTML, requires a context-free language. They match arbitrary depth nesting. You can think of it as a state machine that also has a stack. When you generate what you're going to send and receive, generate your parser from the grammar of the language itself instead of writing it loosely. If you're implementing a program that accepts SQL queries, and you know you're only going to use a subset of available SQL queries, then write your validator to only accept those queries. If you're never going to accept an administrative delete, that's not a valid input. Protocols and file formats that are Turing-complete input languages are the worst offenders. For them, recognizing valid or expected inputs is undecidable. No amount of programming or testing will get it right. A Turing-complete input language destroys security for generations of users. Avoid them. For context-sensitive languages, you need a linear-bounded automaton. It's a Turing machine with a finite tape that still makes it decidable. If you need metadata to interpret the rest of your data, that protocol is at best weakly context sensitive and could be worse. So fixed length strings like IPs, you could parse with a regular expression, but you really wouldn't want to. Unregulated strings like ASN1, you can't even do that. And Turing complete languages are undecidable. If someone sends you JavaScript, the only thing you can do to tell if something is going to leak information out of a WebSocket is to run it or hand audit it. Neither of these really work at scale. Understanding these automata and their concepts allows us to stop weird machines before they're born. So if you constrain the input handlers to context-free or regular, if you can establish that for the software you're writing, then you can really simplify. Another goal here is computational equivalence for all protocol endpoints. When software, jumped too fast. When software components communicate, the messages they send to each other must be interpreted by receivers exactly as they were meant by senders. Otherwise, you get ambiguity, and where there is ambiguity, there is insecurity. Protocol endpoints need to contain computational equivalent parsers. But for non-deterministic languages, for ambiguous context-free grammars and more complex, the task of validating parser equivalence is also undecidable. No amount of programming or testing can get it right. So you can ensure computational equivalence of protocol endpoints by using only regular and context-free protocols. So John Postel was a contributor to the development of the internet itself. He articulated a fundamental principle of software design: be conservative in what you send, be liberal in what you accept. This is why the internet works, but it's also why the internet works the way it does today, and why all of these risks exist. So the Langsec crew has released a patch for Postel's principle, a fundamental principle of secure software design: be conservative in what you send, be definite in what you accept. If we pop the stack and look back at the first stage of the zero logon exploit, it starts off with this problem of the server accepting inappropriate input. Part of Microsoft's response to the zero login vulnerability was to update the NetLogon remote protocol spec. So now, if none of the first 5 bytes of the client challenge is unique, the server must fail session key negotiation without further processing of the following steps: recognize, validate, and then process. It's a great example of being definite in what you expect. The Langsec group has been holding Langsec workshops at the IEEE Security and Privacy Symposium since 2014, and there is so much information at langsec.org. If you go digging back into their archives, the 2015 keynote by Dan Geer is amazing. He has a marvelous habit of putting all of his keynotes and talks on plain text on his website. So this is yet another wonderful rabbit hole you can go down if you desire. About every 6 months or so, I go check it out, and I read everything that's new there since the last time I visited. Another great resource on this page at langsec.org is the DARPA keynote from 2018. And I haven't caught up yet with the papers from the 2020 Langsec workshop, but one of them is a presentation on weird circuits in microarchitecture, the same area that gave us Spectre and Meltdown. So I think that one's going to be exciting. Langsec has links to the proceedings of these workshops, and they also have a bunch of papers, a variety of tools. If you want a slightly easier, more accessible introduction, this talk by Meredith Patterson is a whirlwind tour of various projects and tools for language theoretic security. It's a fantastic timeline over 5 or 6 years of projects ranging from web server implementations to secure projects that can be dropped into other coding projects. But again, not exactly current. So these are the people trying to solve this problem at the source. What can we do in the enterprise security space? Tools like web application firewalls and intrusion prevention systems may protect vulnerable targets, but they're also just moving the attack surface. Can we trust them to do the right thing? Personally, I'm not sure there is anything we can do other than to be aware of the problem, to make sure any code development done in-house follows these principles, to talk to our vendors about the practices that they follow. And I'd love to hear people's thoughts and comments as for what you think that we could do from the enterprise security side as opposed to the developer side. So I hope there are some good questions. I do see that there are a few. Let me swap out and take a look at that.
Thank you, Lisa. Mind-bogglingly brilliant, as always. So just to forewarn you, your second question is going to come from Andy Clark, whom, as you know, is both with Vince behind the Bonrati attack in 1999, which Richard Nealon was commenting on. He said he had sweaty palms. And of course, ex-president of the International Association of Cryptologic Research. So while we bring Andy on stage, I'm going to ask a question on behalf of Carlos, who's been extremely active in the comment window.
Okay, I just want to note before you start with the questions, I want to reiterate, I have opinions, but no background. So I'm absolutely happy to discuss this stuff. But honestly, if there are other people who are better knowledgeable than I am, holler, say it in the chat, because I'll tell you what I know, but I'll also tell you what I don't know. And I expect there'll be more of the latter than the former at this point.
Oh, Lisa, we will, but we also trust completely your candidness and honesty about what you know, and immensely love your opinions on such things. So on behalf of Carlos, who's been very active in the chat window, following on from your penultimate slide, actually, what can we do about the causal root of insecurity in practical terms, given the current state of the ICT industry?
See, this is why I go to COSAC, because I don't have an answer. And I want smarter people than me to help me come up with it. My personal answer is, I didn't even know this existed until 10 years ago. And I wouldn't have expected that it was still a problem today. I mean, I went down an 8-year-old rabbit hole, and then I found the RERSEC keynote, and then I looked at the zero login articles and went, crap, this all goes back to the same thing. Once you start to see this, you see it everywhere. So my answers are awareness and reaching out to the people at ground zero, talking to people who code, talking to the people who acquire software for your organization, to talk to your vendors about secure software practices, and looking at what you can do to recognize from the inside when you've been vulnerable to these attacks and what steps you might take in the future to address them. So that's my opinion, but I welcome every other suggestion.
Thank you, Lisa. I'm sure we will get some both in the chat window and hopefully on networking immediately afterwards. But first, before that, the stage goes back to Andy Clark. Andy?
Lisa, how cool was that talk? I really like that. Thank you so much. And it's a really great talk to close off this COSAC Connect. Really impressed. You really caught my interest when you mentioned that crypto failure at the very beginning of the talk. And so I promise I'm not making a crypto statement or asking a crypto question. I was actually just interested in how a crypto failure like that actually gets through into a widely adopted standard. So I had the idea that maybe that was because we get incredibly siloed in our work. We have mathematicians next to crypto specialists, next to safety critical software developers, next to people who do agile. And so we work in these silos and we chuck stuff over the wall and say, okay, there's an algorithm, go do it. So I wondered if you had any idea about how we can get better at solving that problem, maybe by lowering the silos, maybe working in an interdisciplinary way. Now, you've got a load of experience in the industry. Have you got any ideas?
I do, and this is one that I feel qualified to have an opinion on. Thank you. I believe that every discipline in IT, whether it's software development, whether it's enterprise security architecture, whether it's network design, all of these disciplines are lacking in what I consider to be layer 8 clue. Whether that you call that the personal layer or the political layer, we all get so focused on the problem that we're trying to solve that it's hard to pop up and look around ourselves and say, this activity being done by the person next to me is directly relevant to what I'm doing, and what I'm doing affects these other 3 people. It's not only hard to bring ourselves to do that, but okay, now we've recognized it. There aren't structures and formats and frameworks in place to support us doing anything about it. So you identified the answer, interdisciplinary working. And also, I am a medieval studies major. Effectively, the reason I am functional in technology is that I see all of this as systems of systems.
Yeah.
We tend to promote people who have very specific domain knowledge. But what we need to be doing is wrapping those people in systems thinkers who can see how this person fits to that person, fits to the other person. And we need to be valuing the expertise and the context of those design thinkers, dare I say, to bring the larger picture into focus. So that's my opinion.
Maybe we just need some humility as well.
For sure. I always need that.
Cool. Brilliant. Thanks, Lisa. Really cool.
Thank you, Andy. I'm so glad you enjoyed it.
Yeah, great.
Thanks, Andy. Once again, brilliant answer, Lisa. Thank you. Got another no-stage question, once again from Dimitri, how his brain is operating at this level at what must be 4 a.m., I think, in Australia is quite extraordinary. He says, have you thought that the similar problems affect humans who are biological computers? As an example, magicians are exploiting inputs of the audience to trick them.
So first off, I want to recognize Dimitri as some of consistently the best questions throughout all of these sessions. And secondly, oh my God, yes. This is
who, by the way, has never made it to COSAC Ireland, but he has been to COSAC APAC. So
this actually motivates me to try to get to COSAC APAC so I can meet you and talk with you in the hallway. We need to be better as humans at input recognizing and parsing before we act on input. So I absolutely believe that this extends out of the coding domain and into the social interaction domain, for sure.
Lovely. Thank you very much indeed. And thanks once again for the question, Dimitri. Going over to Martin Hopkins. Martin?
Can you hear me?
Yes.
Good, excellent. Yeah, this goes back a long way. It takes me back to, I guess, the 90s when I was working on CPU emulators and actually having to try and actually re-implement some of these things, which is an even crazier thing. How many of these things do you think are actually not the result of, I guess, developer ignorance or indifference or error, but they're actually about the company being competitive? So it's about getting product to market, it's about being optimal. I think if you look at something like Spectre, that's possibly an optimization that nobody really thought through some of the consequences of, but it was an intentional optimization.
Oh, absolutely. You should totally talk to Mike Broom about this, first of all, because he will have even stronger opinions than I do. But I would say, absolutely, there are pressures to be innovative. There are pressures to deliver a product. And these lead to, and I've stolen this concept entirely from Mike, these lead to developers who go out and they go find someone else's solution to a problem and they plug it into their product. I don't need to reinvent the wheel for this function when I can go find an example of it that someone else wrote and reuse it, whether that's open source, whether it's the answer to a question on Stack Overflow. So this is both partly how you get shotgun parsers, because you're plugging in bits of code from everywhere. And it's also necessary in some cases. If you tell a company they have to implement everything from scratch, that's going to be a competitive impediment. So how we get the frameworks in place to protect programmers from the effects of these issues while not slowing them down or making them unable to innovate is a hard problem in computer security.
Shall I go ahead with my second question, David?
Yes, please, Martin, go ahead while you're on
the floor. I think the other question was around what about sort of temporal and environmental issues and how they relate to weird machines. And I'm thinking back to a couple of examples. It's probably again back to the 90s where it was a Microsoft compiler actually, and it selectively and silently disabled optimizations based on how much memory it had available to it.
Of course.
So the output actually varied. And the other one was actually while working on some network drivers, 10 gigabit Ethernet drivers, and some strange effects where all of a sudden, and you could actually manipulate it, you'd have DMA timeout, DMA overruns. So you wouldn't actually get the memory onto the wire quick enough or off the wire into memory quick enough. And there were some really strange error cases around that.
Absolutely. Those are environmental considerations that I didn't even know existed. And I can completely see how they're relevant to this. Thank you for bringing them up.
Even with your bytecode and the same interpreter on the same hardware, it's not deterministic execution.
It just kind of makes you want to say, is this problem even solvable? This may be an undecidable problem in computing.
I think it's insolvable in the short term.
How do you detect it?
when something goes wrong.
Isn't that too late?
So I guess that points to when you see an inexplicable error, making sure you get to the root of that error and making sure you understand the causes of that error, because they may point you in a direction that we didn't even know to look before.
And not assuming that it's not actually something that is inexplicable and something that can't actually be manipulated.
Perfectly fair.
I'm thinking about some of the strange, air gapped issues where you've got communication across air gaps via some really weird mechanisms.
Yes.
And it's actually
advanced technology, right?
It has to be wholly controllable.
But you need to know it's there before you even know you need to control it.
Yeah.
Okay, thank you for both questions, Martin. Really appreciate it. We have Mr. John O'Leary back on stage, who's going to ask a question suitable to all of us old farts, aren't you, John?
Yes, definitely. Lisa, this is great information, really great stuff. The question is, how easily exploitable are these flaws? And how many of them have we actually seen in the wild? It's a lot easier to convince the suits to fund awareness and new software and new hardware, sometimes even more people, than to get them to understand any of this. But I still love the presentation. How do we get them to understand it?
So A, I'm so glad you enjoyed it. B, I'm so glad I wasn't giving this talk a month ago, because I would have been sitting here going, it's actually really hard. And C, right now, you hand them the article on zero logon.
Yeah.
And then you talk to them about, that's the tip of the iceberg. Here's all of the iceberg underneath. And the suits may not need to see the whole, do not need to see the whole iceberg, but they need to understand
it. Yeah.
But so it's our job to be that curation device for them.
Okay.
We identify an issue, we find something that we can give them that they will resonate with, and then we have to have recommendations for how to address it without requiring them to understand the underlayer.
So we have to understand it well enough to be able to give them recommendations too.
And we also need to be a little discretionary. I would not tell people that they need to go out and protect against attacks on Dwarf on a day-to-day basis. But when you have, or the Ethernet injection, that's not going to be happening in most people's networks. But looking at areas where you have vulnerable protocols exposed, look for the low-hanging fruit, same as any other cybersecurity principle.
So Lisa, can I follow on from that with a comment that didn't become a question? And I'm asking it with my usual obnoxious CEO hat on. So Valerie posted, "Cool job, Lisa. I would love to ask a question, but I feel extraordinarily out of my depth." And I added a comment. Then the question is, Lisa, can you explain this to me in words of less than one syllable so that I'm no longer out of my depth? No pressure.
Yes.
Sorry about that. What does it
yes,
mean
I can.
to me as a CEO?
The root of all insecurity is that tools that we put in our environment to enable us to function as a business can do things we don't expect. There's a class of attacks that are based on making assumptions about what a program will do and what it won't do. And we need to recognize that these attacks can be defended against at a low level in software development. And when we see them in our enterprise, we need to explore them deeply enough to understand the root causes and figure out whether we can mitigate against it. And Valerie, I feel you. I have spent 2 years reading papers and watching talks and trying to dig into this, and I still only understand about 30% of it. But what I've realized is I don't need to understand 100% of it. I need to put it in front of smart people like Mike and Martin and other people who code. And also I need to make it visible to other enterprise security architects so that you can see the same iceberg I see. And then we can start waving those flags.
Thank you, Lisa. There's also a second comment on the chat that really fascinated me just while we're getting Peter and Noor ready for stage. It's from Miroslav. Hello, Miroslav. Great to see you on board again. Socio-technical analysis is needed. humility of mathematician and technology people is badly needed when dealing with complex real-life problems. You seem to me perfectly qualified as the person to expand on that.
I think that all of us understanding that there are a lot of practices that happen today because they're the way that we're used to doing things that expose us unnecessarily. And identifying these exposures is incredibly difficult, let alone defending against them. So we all really need to work together to recognize the vast area of the problem space that we don't understand, and we plug in, as Andy said, someone who does math, someone who does crypto implementation, someone who does input acceptance, input recognition, execution, get these cross-functional conversations going so that we can start to build that web of protection at every layer that this problem affects.
Thank you, Lisa. I see Peter Seedsma taking the stage. Peter, we missed you terribly when you were in Vegas last year. Do you have one of your usual t-shirts on before we go any further with complex technical questions?
Yeah, sorry about that. Actually, I think I have a relevant t-shirt on. It's something about trusting the new computer overlords.
Yes.
Because that's where we are. My question, Lisa, won't you say that Meltdown and Spectre already kind of made executives aware that computers can do weird stuff? Because in my experience, that was for me it was not new. I think for a lot of us it was not new, but it broke. I saw a lot of panic over Christmas a couple of years ago.
There's a lot of panic, but there's also a lot of what can we do? I mean, if your CPU is doing things that you didn't intend it to, you can't protect against that at any layer in software, really. So we're in this paradox of we can't trust the computer and we have to trust the computer. And the boundary layer between the two is we need to operate with the understanding that both of these things can be true at the same time. And we really just need to try to figure out what structures of visibility and what layers of defense we can put in place so that when problems like this happen, we can catch them early and we can drill into them and we can figure out if there's anything we can do. Sometimes there may not be. That's the real challenge.
Yeah, I think the only thing that pops to mind this quickly is that you can only compute then in three branches in complete different code and hardware, and the winner takes it all.
And is that feasible in the real world? I mean, the other thing is we're all working with a fixed security budget, a constrained set of resources, the requirement to get things done faster and cheaper. So it's a really delicate balancing act.
Even in Navy ships, they cannot do it, apparently.
Yeah. Yep. Thank you.
Thanks a million, Pete. Oh, sorry, Lisa. Go ahead.
I was saying the same thing. Thank you.
Thanks.
Great to see you, Peter. Thanks very much for your question. Just before we go to Carol, I'd like to bring in a question from Noor, who didn't get a question asked earlier on. So if you don't mind, Carol, hold on a second. Noor says, do you believe design thinkers in layer 8, as you aptly put it, should be the focal points to address exploitation at its root? Or what, in your opinion, are other areas on par with the threats language security deals with?
Oh my gosh. I believe that it has to be tackled from both directions. So I believe that the layer 8 thinkers need to bring together everyone else. But I think that the fundamental way to address this with the people who are designing hardware, if you're talking about microarchitectures, that are writing code, if you're talking about the layer 1 through layer 7 challenges. So I think it's really a full spectrum. It has to involve both ends working towards meeting each other in the middle.
Thank you. Carol, thanks for your patience. Stage is yours now.
Hey, no worries. Hey, so I've heard you say, well, if we put checks and balances in coding, that could help. So I would say, well, what we hear a lot is shift left nowadays, put security in earlier. Are there thoughts around this to make, well, if you have a big problem, you start chipping away at it, eat an elephant one bite at a time.
Yes.
If I would want to to educate the developers in my company and only make sure that they indeed do the things that are in their remit to ensure that these problems do not appear in the layers they're responsible for. I can't cater for world peace, but I can indeed. Something like the OWASP, which has been very successful in common code issues. Is there something there which could be used to educate them and push them in the right direction?
Yes, and it's go to langsec.org. The Language Theoretic Security Group has a wealth of resources, and that is for any developer who wants to learn more about this. What I tried to do in this talk was present sort of a review of what much smarter people have put together, and langsec.org is where you find the smarter people.
Yeah, but I think we need to make it simple first.
Yes,
in order to get them over the bridge, and once they realize the problem and they get hooked, then we can say, okay, you coders, you're much smarter than I am. Go in depth, and that's also where I think OWASP was very successful in making it in a way that even I can tell people about common coding issues where I can't code at all.
So if there's one tool for that, it's go watch the Science of Insecurity talk from ShmooCon 2012. If you do nothing else, that one talk is what opened the door for me on every other piece of this.
Please send me the link.
Yes.
Okay, thank you, Lisa. Great talk.
Or even post it in the chat. Thanks, Carol. We have time for one more. It's Lynette Hornung. Hello, Lynette. Great to welcome you. Lisa's comment about system thinkers and the additional discussion is especially relevant to breast cancer treatments in the United States, where some doctors tend to use one approach and fail to listen to the individual patient to modify the treatment with regard to the patient's system, with disastrous consequences for the patient. Thank you for a great presentation, Lisa, and the great follow-up questions. Thanks, Lynette.
Oh, this principle applies everywhere. Like I said, once you see it, you can't stop seeing it. So we talked about how it applies for coding and for enterprise security and for social engineering. It applies for medicine. It applies for any place that you have one entity that needs to communicate with another entity, whether that entity is a program or a system or a human. Mm-hmm. We would do well as human beings to do all of these things, to recognize before we parse, to determine what inputs we will accept and not accept. I mean, so very briefly, up until March, I had been 80% travel, 4 days a week on the road, generally for 15 to 20 years, 18 years, let's say. And I had 80% travel to shelter in place. And what I learned is that my ability to interact with another human being 24/7 really needed some work. So I had to learn to work on my parser, my personal way of understanding what Mike was saying to me and what I was saying to Mike, so that we could make sure that what one side means is what the other side hears. It's a crash course in interpersonal relationships. And I think that's absolutely true, not just with me and my life partner, but with me and my coworkers, with me and the people that I talk to about technology, potential customers of my company. It applies at every layer.
It's in a very different language. It's an issue I struggle with on Thursday afternoons on every SAPSA Foundation course, that interdomain trust thing. How on earth do you cross the boundaries between those different elements of a complex system? How can it possibly be done? It's a hell of a challenge.
This is where my background in medieval studies becomes relevant to a technical conversation. When you read a piece of medieval literature, you're reading it. If I can't read Middle English, let's say, or Renaissance Italian, medieval Italian, but I want to read the Inferno or I want to read Chaucer. So I have to recognize that when I pick up a book and start reading it, there is what the author intended, the cultural context of the author, what the translator brought to it from their cultural context, and what I bring to it from my cultural context. And the medieval studies professor who got me hooked on the Middle Ages those were the two most valuable things that he taught me. One was you have to parse at every layer and recognize at every layer. But the other was everything is a system, and you cannot understand anything until you see its interconnections. The more you can bring in those interconnections, the more deeply you can understand the thing that you're talking about.
I think that's a brilliant statement on which to finish. Just before I go, though, somebody posted a comment just a little while ago, said, I resemble that human being. I think his name is Mike Broom. How far away is he sitting at this moment?
He is downstairs, and he's been extraordinarily patient with basically my BS decompressing, detoxing from coming off the road. So I really appreciate his support in all this.
I can relate. So thank you very much, Mike, as well. Lisa, absolutely fabulous as always. Thank you very, very much indeed for closing the first ever COSAC Connect in such a fashion. Just a couple of comments before we all go. The videos will appear on the COSAC Connect website for all sessions, probably within 48 hours. So you can watch them on demand or relay them to other people. We will send everyone a feedback form link over the course of the next day or so. We really genuinely appreciate your feedback. This is our first attempt at trying to run COSAC and anything like COSAC in a virtual form. So I personally will read every single one of those forums, as will the whole team. Your information you provide on those forums is of enormous importance to us moving forwards. The discussions, as always, will probably run on social media for a little while, so please do feel free to engage on the social media platforms. The networking lounge is now open, so that I didn't get a chance to attend much yesterday, but the people who were there tell me it was a great platform and a great interaction, and it had a wonderful vibe. So please click the link that Kerry has just posted into the chat window, and we'll see you in there for more detailed discussion. And finally, please do stay tuned to COSAC.net and our decisions and announcements about future COSAC Connect events, and of course, full scope COSAC experience when we have that opportunity, when the world allows us to have that opportunity. And we very sincerely hope that those of you who have joined us for the first time have gotten at least a small flavor of the depth of COSAC and what it can provide for you in a full scope experience. So all that really remains for me is to say thank you very much to all of our presenters, all of our question askers, everyone who did comments. Thank you all very much for being here and sharing my passion. And hopefully we'll see you all in the networking room in a few minutes. Thank you very much indeed, everyone. Have a safe night.